Hôm nay là tôi thấy một hiện tượng thân quen và năm nào cũng thấy. Có nghĩa là lớp bao giờ cũng vắng sau buổi kiểm tra.
Nhưng mà thầy có biết lý do tại sao vậy?
Sao?
Em không nghĩ hỏi là thầy có biết lý do tại sao?
Thường đấy thì là các bạn sau khi thi xong các bạn có tâm lý là hơi relax một tí. Nhưng mà cái vấn đề nó lại là đây chưa phải kỳ thi cuối kỳ. Đó. Tức là các bạn cứ dồn vào, giống như là kể cả khi mà tôi dạy tutorial cho các bạn, nhất là buổi cuối này, thấy các bạn cứ lôi húi làm gì, thành ra các bạn đang ôn phần nhiệt trước đấy. Thế nhưng mà các bạn lại quên mất là kiểm tra giữa kỳ nó chỉ tính có 30% thôi. Cái bài quan trọng nhất nó là cái cuối kỳ thôi, nó chiếm tới 60% cơ. Thì lúc trên lớp thì các bạn không nghe, các bạn chưa nghe, và các bạn bảo là em dồn sức trước để kiểm tra tốt cuối kỳ. Thế nhưng mà rất nhiều bạn ở trong những cái trường hợp như vậy thì các bạn lại quên mất, các bạn lại không tập trung được vào cái phần kiến thức mà đáng ra nó chiếm 60% cơ. Đó, bởi vì nó sẽ khác đấy, nó sẽ khác với cái chuyện là ok bây giờ tôi dồn sức vào tôi ôn cái này, sao tôi lại dồn sức tôi ôn cái kia. Nhưng mà có những cái kiến thức nhiều khi chỉ ở trên lớp đó, khi mà trao đổi với thầy, khi mà trao đổi với các bạn ở trong lớp ấy, thì các bạn mới vỡ ra. Còn sau đó khi các bạn bắt đầu các bạn ngồi một mình ấy, thì nó rất là khó để các bạn hiểu. Bởi vì trên lớp các bạn không hiểu, các bạn có thể hỏi luôn. Ở một mình ấy, thì các bạn phải tự tìm câu trả lời, và đôi khi các bạn không tìm ra được câu trả lời mà các bạn quên. Cho nên vì sao hồi tôi ở bên Pháp với cả bên Luxembourg họ rất là đề cao cái chuyện học nhóm, không phải là học một mình mà là học nhóm. Hầu hết các bài cấp môn, nếu như mà có thể làm được theo hình thức hoặc là làm project, hoặc là học nhóm, hoặc là làm nhóm, thì các chương trình đều hướng tới. Và thường là kết quả nó cao hơn, nó không phải là bởi vì vấn đề là các thầy thấy relax hơn, mà thường là cái kết quả của nhóm đưa lại nó sẽ cao hơn kết quả của một cá nhân. Là vì thế một cái report do một bạn làm ra, nhiều report rất dở, rất ít report có thể làm tốt được. Nhưng vì sao một report của một nhóm làm ra nó vẫn luôn tốt hơn ạ? Đúng không ạ? Nó riêng về cái phần là hỗ trợ nhau, nó còn là cái chuyện là khi mà một công sức tập thể thì các bạn có thể tận dụng được, ok người này mạnh phần này thì làm phần này, người kia mạnh phần kia thì làm phần kia, hỗ trợ. Thế tuy nhiên để cái bước đó thì chúng ta phải qua được cái bước đầu tiên là tất cả các bạn đều có cùng một cái binh như nhau, là cái 5-1 này. Cho nên 5-1 vì sao tôi không thể để các bạn mà thi nhóm được. Bài kiểm tra hôm qua thì có dễ không ạ? Nó cũng không nằm ngoài những cái chúng ta đã xem với nhau, đúng không? Đúng không? Không có cái câu hỏi nào mà các em quá bỡ ngỡ, bởi câu này đã học được mà cho thi, hay là phần kiến thức này nó sẽ rơi ở đâu ra. Cho nên là kết quả này thì tôi sẽ công bố sớm cho các bạn trước kỳ thi cuối kỳ, kể cả về phần điểm danh, kể cả về điểm bonus, kể cả về điểm giữa kỳ. Sau Tết các em sẽ có lịch thi, các em chú ý là lịch thi sẽ đưa lên khá là sớm đây.
Mà lại chưa có danh sách lớp, ngày mai thi.
Phổ điểm hôm qua tôi xem thì không tệ đâu. Phổ điểm tôi xem hôm qua thì không tệ đâu, không tệ như mọi năm. Có thể là năm trước thì mình khó đánh giá bởi vì là Covid, nhưng mà năm nay thì hoàn toàn không tệ. Ít nhất là cũng phải có Nếu mà tôi xem đúng thì cũng phải 60-70% là qua đấy. 70% là qua.
Là qua.
Bình thường mọi năm là 50%. Cho nên là năm nay là tôi xem phổ điểm của cả hai nhóm khá là ổn. Thực sự là thấy cũng khá là ổn. Qua là tôi bắt đầu tôi tính từ 5 đấy nhé. Nên là và phổ điểm nó phân bố rất là đều. Cái chúng tôi quan tâm là phổ điểm nó phân bố đều, nó như thế này. Chứ nếu như mà giả sử nó lệch hẳn về một bên như thế này thì là đề thi là có vấn đề, hoặc là các bạn có một cái cách thức nào đó các bạn hỗ trợ nhau rất là tốt. Còn phổ điểm thì nó phân bố rất đều như thế này. Có thể là cái phần trung tâm này nó lệch đi một chút, nó lệch sang đây thì là tốt, nó lệch sang đây thì là không tốt. Thế nhưng mà nếu mà phổ điểm nhá, nó mà phân bố như thế này, hay là nó phân bố như thế này thì là đề thi không tốt. Cho nên các em vì sao mà thấy sau mỗi lần Bộ Giáo dục và Đào tạo tổ chức kỳ thi quốc gia ấy, họ đều công bố phổ điểm đấy, họ đều công bố phổ điểm lên toàn quốc. Bởi vì mọi người sẽ biết nếu mà ta có một cái phổ điểm như thế này nghĩa là sao ạ? Và hoặc là đề quá dễ, hoặc là kỳ thi có vấn đề, đúng không ạ? Kỳ thi có vấn đề thì nó mới có thể có một cái phổ điểm mà lệch hết về dưới như thế này, tức là gần như là chả phân loại được. Bởi vì sao? Thi cử ngoài mục đích đánh giá, có nhiều kỳ thi còn để mục đích phân loại, đúng không ạ? Ngoài là đánh giá ok, anh đang ở mức này, anh đang ở mức kia, thì một tính năng nữa của kỳ thi, tất nhiên là không phải kỳ thi của chúng ta, nhưng mà ví dụ như kỳ thi vào trường, kỳ thi học bổng hay là gì đó là mục đích phân loại, đúng không ạ? Tôi loại người nào giỏi, người nào kém thì tôi loại, người nào giỏi thì tôi lấy. Đó. Ok, các bạn bây giờ ta bắt đầu nhé. Các bạn đóng hộ tôi cửa này vào. Nhưng nói chung không tệ, năm nay không tệ. Năm nay sau khi thi xong tôi xem qua thì hoàn toàn kết quả không tệ, cho nên không phải lo lắng. Nhất là các bạn, những bạn nào chăm học ấy, thì các bạn đã có 20% số điểm vào trong tay rồi, 10% attendance và 10% bonus nhân bảng. Nên là tôi nghĩ là hoàn toàn không phải lo, cứ tập trung như vậy. Đề cuối kỳ thì chắc chắn nó sẽ khó hơn đề giữa kỳ. Nó khó hơn ở cái việc là các bạn sẽ phải ôn toàn bộ các phần kiến thức mà chúng ta đã học. Đó. Nó không phải khó hơn ở cái chuyện là tự nhiên bài nó lại khó hơn một cách đột ngột. Nhưng mà cái lượng kiến thức mà các bạn phải nhớ, các bạn phải vận dụng thì nó nhiều hơn rất là nhiều. Toàn bộ phần cơ học và toàn bộ phần nhiệt động lực học. Rồi, bây giờ tôi đề nghị các bạn ta tập trung nha, chúng ta bắt đầu vào lớp. Hôm qua thì đông thế, ngồi không có chỗ ngồi đấy, hôm nay thì chỉ được nửa ấy. Cuối kỳ thì sẽ chia ca nhỏ hơn. Được chưa ạ? Ta tập trung được chưa ạ? Tất cả các bạn. Các bạn có máy tính như các thứ đây ạ. Ta tập trung nhé.
Không thấy người ta.
Rồi, ok các bạn. Buổi hôm nay ta sẽ học hết mà. Hôm nay là chương cuối rồi. Các bạn chú ý thì thấy là bao giờ tôi cũng dành 10-15 phút đầu để tôi nhắc lại cái phần mà chúng ta học trước. Kiến thức khi mà ta xem một lần thì có thể ta chưa ngấm được vào đầu, ta xem lại lần thứ hai ta sẽ vỡ ra nhiều thứ. Tới lần thứ ba ta làm cùng nhau ở trên tutorial đấy, ở trên các lớp bài tập thì chúng ta sẽ vỡ ra rất là nhiều điều, và sau đó lần cuối thì ta ôn thi lại trước khi thi. Đó. Ok. So could we start?
Yes.
Yes. Okay. Please make no noise. So I think it is a good thing that we recall what we have learned last time together from here. The model specific heat at constant pressure and at constant volume. Okay? Because some people say, why do I need to study this one? And I answer, it's just like when you build a system, you need a lot of parameters. So you need the length, you need the volume of the system, you need all the things. Here, if you know the Cp and Cv of the substance, you should be able to know how much heat should we provide, should we supply to our system, for example. So these are important parameters when we consider the thermodynamics. So the Cp and Cv, now we know, okay, the expression of the Cp and Cv. Here, this is, okay, I go to here better. I think I have a table that summarizes everything, right? So I think we start from there. Maybe we start from there. So this is the first law. This is the change in internal energy for an ideal gas. For every case, every process. We have this one. This one we can apply, right? For every case, we can have this one. Remember, and Cv delta T, we can apply for all cases. Because only the Cv will help us change the internal energy of our gas, of our system, not Cp, okay? The difference between Cp and Cv is to do work. So this one we can apply. And remember one more thing. The general formulation of work. So the work equal integral PdV, okay? So I think these are the three most formulas that you will see. First law, this one, and the work, how to calculate work. So for an isobaric process, I mean constant pressure. When we say constant pressure, please, you recall immediately to the Cp. Remember the word P, okay? Constant pressure. Constant pressure we call isobaric. Iso means constant, okay? Bar. Remember that the pressure can be measured in bar also. The isobaric is constant pressure. When we have a constant pressure process, we use Cp, okay, and not Cv. We use Cp to calculate the heat added or removed from the system. Because at that time, the heat supplied to the system is to do two things. The first thing is to increase the change in internal energy of the system. And the second thing is to do work. Okay? So this is for constant pressure, also called isobaric. The work, of course, we know that this is the product of P delta V. Okay? For isothermal, I mean constant temperature, then we know that the change in internal energy should be equal to 0. Why do we have this? Someone explain? Why do we have this one? For an isothermal process, why do we have the change in internal energy equal 0?
There's no change in temperature, so no change in energy.
Why? So, remember here, how do we calculate the internal energy? Remember here. Câu này rất dễ mà lại không trả lời được. Rất nhiều bạn không trả lời được. Here. The internal energy of our gas depends only on the temperature. Yeah. So, if there's no change in the temperature, the change in internal energy should be equal to 0 for that reason. So remember, okay, if you remember that, okay, the change in internal energy of an ideal gas depends only on the temperature, you should be able to answer the question very easily. So no need for you to remember, right? If you understand this. That's why we have this one equal 0. Okay? Once we have this one equal 0, then according to the first law, we have the heat equal the work. Even yesterday, some students still ask me about the sign agreement. Okay, the heat, the work added to the system, the work done by the system, is it positive or negative? Yesterday, after the the midterm exam. So the work done by a system is positive or negative? Huh? Who say negative? The work done by the system. Who say positive? A lot of people. And for the others, you don't know? So you understand why I got like a not good result. Because these are very, very basic and you still do not remember, okay? The work done by our system is positive by our agreement. Đấy, vì vẫn còn ngồi bàn đầu mà còn chơi đọc manga đây này thì làm sao mà thi tốt được?
Nó là
Thấy chưa? Tới bây giờ vẫn còn chỉ cho thanh niên này từ đâu? Từ rừng về à? Hay từ đâu? Thanh niên này bây giờ vẫn còn chỉ cho tôi một cái source ở trên mạng. Thầy ơi, cái này nó ghi là work done by system is positive. Bạn nào giải thích được cho tôi ạ? Tức là nếu bạn thấy một cái source ở trên mạng và nó ghi là the work done by your system is negative, và bạn chỉ cho tôi, vừa chỉ cho tôi xong, bạn nào giải thích cho tôi vì sao ạ? Vì sao có sự khác nhau thế ạ?
Do tùy công thức ạ. Có một số công thức thì họ sẽ viết là dấu cộng, nên là khi mà xét theo các trường hợp work done on với cả work done by thì sẽ khác nhau.
Vâng ạ, quy ước về dấu ạ. Nếu mà bạn xem ấy, thì bạn xem kỹ hộ tôi là cái công thức lúc đó nó viết như thế nào ạ. Nó sẽ không viết là delta E bằng Q trừ W ạ, mà lúc đó nó sẽ viết là delta E bằng Q cộng W ạ. Hoặc là nếu không thì nó ghi thành delta U bằng Q cộng A hay là gì đó đấy ạ. Cho nên là khi ta xem, một là ta lắng nghe ở trên hội trường, hai là nếu mà ta về ta xem thì ta phải xem cho tận tình, ta phải xem cho kỹ ạ. Lúc đó công thức của nó tiên tôi đi, nó sẽ là delta U bằng Q cộng A hay là gì đó. Không thì ít nhất nó sẽ là delta U bằng Q cộng W ạ. Lúc đó nó sẽ không phải trừ ở đây, bởi vì họ quy ước khác chúng ta. Họ quy ước là W là work done by a system is negative đấy ạ. Thế thì công thức của họ sẽ phải ghi là delta E bằng Q cộng W, về bản chất thì nó không được. So, by nature it doesn't change anything because this is just the agreement of the sign. We agreed that okay, we say that the work done by a system is positive, then we write change in internal energy equal heat minus, okay, minus the work. If we say that, okay, I want to use the agreement that, okay, the work done by the system is negative, then I should write change in internal energy equal the heat plus the work, right? So the sign agreement will help us. I do not need to specify any time I use it. So once I already have the sign agreement, I can write only the letter W. I do not need to specify every time, okay, when I write this one, the W is the work done by the system and so on, or the work done on the system. Remember? Cái này tôi nhắc rất nhiều lần rồi. Chỉ có những bạn nào không để ý thôi thì mới hỏi tôi những cái câu như thế. Được chưa ạ? Các bạn nhớ thật kỹ phần này nhé. Chứ tôi không muốn là tới sau kiểm tra rồi vẫn không biết là tại sao mà lại có sự ngược nhau như thế này. Tại sao nó cái shortcut? Tại sao trong hóa họ lại ghi là cộng nhỉ? Tại sao trong lý lại ghi là trừ? Dễ lẫn lắm. Nhớ nhá. And of course, this one you remember the adiabatic, a very interesting phenomena in thermodynamics. So we have two constants. A little bit hard to remember. We have two constants, P, V power gamma, and T, V power gamma minus 1. A little bit hard to remember. Okay? So we understand why last time we have this, and we have this. But in short, you can just remember that, okay, for an adiabatic process, this one is a constant and this one is a constant. So, the heat, of course, of an adiabatic is 0. And the work is minus delta change in energy. Okay? Isochoric. The isochoric process, it means constant volume. Constant volume. Isochoric means constant volume. The work equals 0. Do I need to re-explain why? I also explained a lot of time already, right? Now you accept. Now you understand. That's why we have the work equals 0. Hả? Bạn nào đóng hộ tôi cửa ấy. Then, according to the first law, we have the heat equal the change in internal energy and equal NCV delta T. Right? Equal NCV delta T. If you are able to remember this table, it will be very helpful for you. You do not to re-establish these formulas. And believe me, if you cannot remember this short table, I don't think that you are able to re-establish these expressions during the exam, especially. You do not have enough time. Better to remember it and to understand also why do we have this. Okay? The most important thing is to understand why do we have this one. Okay? When you remember it, it's good, but the most important thing is to understand why do we have this one. Is it okay? Good. Did we do this time? Did we do this one last time? Bài này làm chưa? Bài này làm. Lần trước làm chưa? Okay. So I invite you to try to do this one. In few minutes. You better have your notebook or something to write it down. Qua các bạn nào tự tin là mình được 20/20. Tôi thấy có một số bạn được 20/20 đấy. Không nhiều nhưng mà cũng được vài bạn đấy.
ไม่ได้ต้องการว่า
So, in this exercise, we have an ideal diatomic gas. Good. Here, this is the tip. When you see the word ideal, okay, you remember of the ideal gas law. It might be useful. When you see the diatomic, you remember that we have a degree of freedom of 5. When we have the gas, okay, you remember about the first law also, the first law. An ideal diatomic gas. The first step, you write down the 3 formulas that you might have to use before the exam. The ideal gas, the first law, okay, ideal gas, first law, and the change in internal energy, and F over 2R, because we have the degrees of freedom. So this is what we know on ideal gas, this is what we know on diatomic gas. Then we also know the pressure, the initial pressure and the initial volume. The book. This is what we need to find. When okay, we need to find the work, we need to find the change in internal energy. When it expands adiabatically, so we know that we have an adiabatic process. Please do not show me this, because I do not remember the results. You have to be sure that, okay, you have a good result. Okay? If you are sure that, okay, this result is good, then it's good for you. It doesn't change to me, it changes to you. So do not show me, okay, here, I have this is for you. If you are able to do it, well, it's good for you. Bạn nào còn ngủ thì đi ấy đi ạ, đi rửa mặt đi ạ. So I see one can already done it. So we try to see step by step. some people did not do the job, but look directly to the exercise. But the problem is that if you do not understand, it will not be helpful if you just look at the solution. Because during the exam, you will have no solution to look at. Here, what we have for the assumptions. Firstly, we have the ideal diatomic gas. The initial volume we know. Okay, this the initial pressure we know. The final volume we know. And we also know that this is an adiabatic expansion. Then we should be able to calculate this ratio, right? Why do we have this ratio? Why do we have this one? Can someone explain to me?
CV bằng gì ạ? CV yếu.
Who can answer it? Why do we have this one? You see, you need more time. So, remember, for a diatomic gas, okay, for a diatomic gas, what we have? We have the degree of freedom, which is equal to 5, right? Then we should be able to calculate the Cp of a diatomic gas. The Cp of a diatomic gas. Last time I told you that. Okay, even last time we did this one. Okay. Last time we also did this one. Remember the degree of freedoms. We have a direct relationship with the Cp and Cv. For diatomic gas, the degrees of freedom is 5 because we have 3 translational freedom and 2 rotational freedom. Here, and we know that Cp and Cv will have a difference of R, right, of the gas constant. Of the gas constant. Cp and Cv. Cv và Cp nó khác nhau ở một hệ số R đó. Cái này thì rất dễ nhớ. Và các bạn nhớ là Cp và Cv nó có thể được tính dựa trên cái bộc tự do của cái khí của các bạn. So we did this last time. Now you understand why we have this one, right? Đúng chưa? Các bạn bây giờ hiểu chưa? Hiểu vì sao ta có cái hệ số này chưa? Trung hiểu chưa? So, this one Cp is for a diatomic gas, okay? And this one is Cv for a diatomic gas. Diatomic gas. What is the ratio gamma of a monatomic gas? Can someone answer? For a monatomic gas, what do we have? So, for a monatomic gas, this time Cp equal. Okay. And Cv? Good. Then the gamma will be 5 over 3, right? For a diatomic gas, we have this one. For a monatomic gas, we have this one. You see, that's why I have to repeat it and I have to be very slowly in this part. Here. So, okay. We continue. If we already understand this, because we need this one, we need this ratio to calculate this formula. We know that we have an adiabatic expansion of the ideal gas. So for an adiabatic expansion, remember here we have two constant quantities, PV power gamma or TV power gamma minus 1. So depending on the assumptions that we have, here what we have is the initial pressure, initial volume, and I think the final pressure, right? The final volume. Then we know that we can better use this constant, PV, and we do not use this constant because we do not know the temperature. If we want to have the temperature, we have to do some development of the formula, and this is not necessary, right? We have this one. We have this one. What we want is to have an expression of the pressure, okay, of the pressure as a function of the volume, as a function of the volume. Good, as a function of the volume. So we know that because this one is a constant, this one is a constant. So in any time, we should be able to write PV power gamma. So PV here is valid for any moment, okay? PV power gamma should be equal to the initial state, Pi Vi power gamma, because this is what we know. So we have to make use of what we know, right? Then, if we are able to write this formula, we are able to have the function. Okay, we have the function. The pressure as a function of the volume. Right? You follow me until here? Đúng không ạ? Vì cái này nó là constant này, nó là không đổi này, thì chúng ta có thể viết được là PV power gamma, PV ở bất kỳ thời điểm nào, đúng không ạ? Nó cũng bằng PV power gamma ở cái thời điểm ban đầu, PV power gamma ở thời điểm ban đầu. Đúng chưa? Và như thế thì chúng ta sẽ thiết lập được cái biểu thức P theo V. P là một hàm của V. Good. Because we have to calculate the work, right? Remember that this is the general expression when we calculate the work. And if we already have the expression of P. Then we replace this. Okay, we replace this to the integral. It seems a little bit hard, but you see, what we know is pi, vi power gamma. This is what we know. We take it out from the integral. Okay? Inside the integral, we have only this one. We have only this expression. And this expression has a mathematical solution. Right? Right? This is mathematical solution. So okay? For now, we forget the pi, vi power gamma. This is the solution. Các bạn nhớ cách giải không ạ? Nguyên hàm ạ. Tích phân của thằng này được không ạ? V mũ trừ gamma dv ấy, thì nó sẽ bằng cái thằng này. Đúng không ạ? Toán cấp 3. Đúng chưa? Cho nên là nhìn thì có vẻ phức tạp, nhưng mà thực ra nó là toán cấp 3 thôi ở đây này. Đúng không ạ? Cái này tính được đúng không ạ? Tính quá được đúng không? Thế thì tính được cái này, bây giờ có cái gì ở đâu? Hay we replace, we substitute the value here. So pi we know, vi we know. This one we know easily, right? Then if you calculate correctly, we have this number. And according to the first law of thermodynamics, because this is an adiabatic process, we have the change in internal energy. This is the level of the final exam. Yeah. If you understand, nothing is difficult. The most difficult part is how to solve it within 2 minutes, that's all. See? Is it clear? Now, to summarize, we have the concept of kinetic theory of gases, we know it. First thing we should remember is the ideal gas law, PV equal nRT. Okay? The work done by an ideal gas, we have 3 special cases. The work done by an ideal gas after the general formulation that we can always apply, we have 3 special cases. Then we should have the relationship between these macroscopic properties and these microscopic property. This one is a little bit hard. Maybe you see less in the exam. The temperature and the kinetic energy, which is easy, right? We remember that the kinetic energy of an ideal gas depends only on the temperature. Mean free path, the average distance that one molecule can travel between collisions, the average distance. Okay? Maxwell distribution, you should know, but I will not include it in the exam. But you should know. I'm considering, I do not decide yet, but I'm considering to remove it from the exam. Molar specific heat, this one is very important. Okay, we have the CP/Cv and degrees of freedom as Cv, the degree of freedom. Sorry, this is a small v, the degrees of freedom. and the CV. Okay? Then the adiabatic expansion of an ideal gas and what we just seen together. Is it clear? Hope it's not too hard. You see, this is a big chapter with a lot of things to remember. That's why I need more than 2 sessions discussing with you. And this is the main part of the final exam. Okay, now we move to the last part. The part of second law. Entropy and the second law of thermodynamics. Maybe before that, we take a break for people who not have breakfast. Please, we see each other. We see after 10 minutes, and we go back to the auditorium.
Đừng có gõ đoán xa như thầy. Ít mẹ mình biểu phụ thế. quite. Tôi đã quay lại sau một cái bánh mì nữa.
Vâng, ta bắt đầu tiếp nhỉ. Thôi các bạn dừng ăn uống đi ạ. Tí nghỉ tiếp ta lại ăn tiếp. Hôm nay chỉ có hút nốt sữa đi ạ. Ơ, bạn nào đóng hộ cho cái cửa nhé. Sao không lên nhỉ? Okay, we try to finish the last part of thermodynamics. Here, for this part, we will talk about the entropy and the second law of thermodynamics, and also some applications. Good. Bạn tập trung được chưa? Này vẫn hơi rì rào. Vào lớp rồi đấy ạ, dừng hết chơi điện tử đi, tập trung lại đi. Rất nhiều câu hỏi dễ rồi thì rất nhiều bạn chưa trả lời được đâu. Nhé, tập trung đi. So, in this chapter, we will talk about the entropy, the second law, and also some very famous applications. Bạn này dừng ăn đi ạ. Đã nói rồi, tí ra ngoài để ăn. Được hết chưa? The two famous applications, the engines and the refrigerators, the applications of the second law. Good. Actually, this is not only the second law. To be able to build these things, we should have the knowledge of the zeroth law, the first law, and the second law, actually. Yeah. So, in this chapter, we discuss a very interesting thing. A very interesting thing, the irreversible process. Irreversible process. We know that from the very beginning, okay, the first session we discussed together, I said that in reality, most of our processes are irreversible processes. It means that we cannot return exactly to the initial state, right? For example, if we drop an egg onto a floor and the egg is broken down, we cannot restore the egg to its initial form anymore. Or when we crash a car, of course we cannot get it back except we pay for money and so on. But for sure, you will not have the new car anymore. You do not have the new car anymore. Đây là cái vấn đề mà thi thoảng đấy, nhưng mà các bạn ô tô, các bạn thấy là ở vùng này đang có tai nạn xảy ra này, xe ô tô đâm nhau, tin thôi thì loanh quanh trong vòng 1 tháng, 2 tháng sau là có xe bán. Ghi ở quảng cáo là xe mới nguyên, chưa đụng bao giờ, ở đúng cái vị trí đó, đúng chỗ đó. Đó. Nhưng mà đấy không phải xe mới nữa. So we try to explain why is it happen? Why is it happen? Why are these processes? Why these processes are irreversible? Right? Why these processes are irreversible? And that's one way for us to explain it. Is by the idea of entropy. By the idea of entropy. Good. So entropy is actually a mathematical way to encode the notion of which processes are impossible, which processes are possible, and which processes are impossible. Ever heard about the word entropy? Đã ai nghe thấy từ entropy chưa? Bao nhiêu bạn nghe thấy trước, hiểu được cái trước? Có một số bạn thôi ạ. Nhiều bạn là lần đầu nghe thấy hay như thế nào ạ? Nghe thì chắc nghe rồi đúng không? Nhưng mà hiểu thì chưa chắc đúng không ạ? Bởi vì phổ thông chúng ta chưa học. So, in very short way to understand, entropy is a matter of the molecular disorder. Okay? We always hear the word disorder when we talk about the entropy. Okay? The word disorder. But how do we understand correctly the word disorder? This is another problem. Entropy is actually a matter of the molecular disorder, or the randomness of a system. I will try to explain, for you to understand correctly the meaning of this word, the word disorder. So this term actually was defined by Clausius in 19th century. Actually, this is a word from Greek, and it means in. Okay? Tropy here. Top is a turning point. In a turning point, then something will happen. Initially, this concept was developed to answer to the observation of what we see in a combustion engine. So they try to explain the energy lost from combustion reactions due to the dissipation or due to the friction. They try to answer why when we burn something in a combustion engine we cannot get an efficiency of 100%. Why do we always have the dissipation and friction? So you see, the entropy comes from a very specific case in our daily life, and then after that we use the entropy in another cases. But before, you may see that it has mostly nothing with what we are studying until now. But it came from a real question. They try to explain why we cannot attain 100% for the efficiency in an engine. Then they try to think of a way to explain. Then they think of the entropy. But after that, the science was quite developed. Now it's like we do not see the entropy with the friction with the engine anymore, because it is becoming evolved. It is evolved a lot for the science. Okay, if we want to understand correctly the entropy, we can define in two ways. We can define it in two ways. I try to explain you both in two ways. One way is to start from the microscopic perspective. And second way is from the macroscopic perspective. Both are correct. So from the microscopic perspective, remember that when we say the microscopic, we think of very small thing, right? We think of, for example, our molecules. Okay? When we talk about macroscopic, we think of something that we can observe, some properties, for example, pressure, volume, temperature, so on. Heat, for example. So, I will start with the first way to define the entropy of the system. Okay, the microscopic perspective. Bạn nào đóng vào tôi cửa với? So, this is by counting the ways in which the atoms or molecules that make up the system can be arranged. I repeat here again. The microscopic perspective, okay, to understand the entropy is by counting the ways in which the atoms or molecules that make up the system can be arranged. So it means, okay, I have my system here. I have my system here. So initially, this molecule will have its position here. Okay? This will have a position here. Good. If something happens, it will change the position, right? So if I consider here this is the initial state, if only one molecule changes its position, then I have another arrangement. Do you agree with me? For example, here I have 16 molecules. 15 are keeping the same position. One changes the position. But for the whole system, I already have a new arrangement. Do you agree with me? Bây giờ giả sử là hệ của tôi có 16 phân tử ở trạng thái ban đầu. Bây giờ tôi cứ coi như là 15 thằng đứng yên đi, nhưng chỉ một thằng nó thay đổi vị trí của nó là ta đã có một cái sự sắp xếp khác cho hệ, đúng không ạ? Rồi, các bạn hiểu cái đó nhé. So, that's why we try to see, for example, here I have an example. Before we have the hot block, after and a cold block. When we get it into contact, we will have more ways, more arrangements of our system. That's why we say that, okay, at the end, the entropy increases. So you start to think, okay, the relationship between the arrangements of my molecules inside my system and what we call the entropy. Okay, you do not need you maybe call the entropy with another word, but okay, that's the relationship between the arrangements of my system, of the molecules of my system, with what we call the entropy. Đi rửa mặt đi ạ, ngồi ngủ hăng say đi, tớ muốn ngủ nữa cậu. Now, we say that the entropy is the measurement of the disorder of the system. Maybe it's hard to see you here, but I give you an example for you to understand better. The word disorder. Please do not make mistake with what we see that okay is ordered or disordered. Here I have the figure of a room, of two rooms actually. One room, you see that, oh, it's very ordered, it's very clean, it's ordered, okay, well set up. And another room is actually messy. My G rooms here, I don't know, the rooms of other one, okay. For example, you see here that, okay, this one is very ordered, okay. This one is not ordered at all. We call it disorder. But we cannot say that this one will have an entropy that is bigger than this one, because this is not the right way when we understand the word disorder. Okay. For example, here another. We have the moon and we have the sun. Which one has more entropy than the other? We do not know. If we look at here, we may see, okay, this one is quite more order than the sun. But it doesn't mean that it has a bigger entropy. Good. the order or disorder is not what we see. It's not what we can perceive by our human sense. Okay? Here maybe the room of my chi has less entropy than this one, we do not know. We have to look at really the waves, the atoms and all the molecules of this system can be arranged. Okay, now to simplify, I consider two systems, very small systems. One system contains 4 atoms, okay, and one system contains 8 atoms. Very simple thing, very simple thing. To try to explain it. Here. Good. Very small. I also have different colors, so you can track it easier. Okay. You see here, if I have only 4, I may have this one, I call it one state. Another state, for example, it can change from this position to this position. And this will go to here. I have another state. Right? Or it can go from here to here, I have another state. But I do not need to calculate. I can tell immediately that, okay, if I do like this, the system having 8 atoms will have more states, more possible states. Am I right? So this one can go not only here, here, here. Now this one can go here, 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 and etc. It might take more position in my system. So more states. And this one also. So you agree with me that this system should have fewer possible states than this system. Am I right? Good. We say here, this system will have more entropy than this one. Yeah, because it has more possible state than this one. So this is the way we understand of the entropy. The entropy should understand by the state, the possible state that our system might have. Yeah. The possibility for my system to have more states. Yeah. So more entropy means more possible state. Yeah. And we can use this word, microstate. Microstate. Boltzmann, him again, he defined entropy as a measure of the number of possible microstate of a system in thermodynamic equilibrium. Good? More possible state. You understand? Good? So do not just look at by the appearance. We should really think of the microstates that our system might have. And the number of microstates is the definition of entropy. Good? Is it okay? Now, if we consider a box that contains 6 molecules, identical, okay, molecules. Identical, these are identical. Good. And you will see that at any moment, so one molecule, a given molecule, can be either in the left or in the right half. Okay, left or right half of the box. Then we can say that the molecules will have the same probability of being in either half. So it can be in this half or it can be in this half, and the probability is the same. Okay? It's the same. Then we might determine the possible configurations of the 6 molecules. You see, for the configuration number 1, 6 molecules are found in one left half, and 0 are found in the other. Okay? So for the second label, 5 are found, for example, on the left, 1 are found on the right, and so on. Here, this is the case where we have nothing on the left, and here we have 6 on the right. Is it okay? You still follow me? Then, if we consider this, the microstate, what do we have? We suppose, now try to do the calculation, we suppose that n molecules are distributed with the number n1 molecules with 1/2, and n2 the others. Okay? Then of course we should have n1 plus n2 equal n. Am I right? Because I still have the totality of my molecules here. Then the total number of ways in which we can select all 6 molecules. Here we have to use a little bit of probability. I show you here. The total number of ways, okay, in which we can select all 6 molecules. Good, is the product of these independent ways. So you use a little bit of probability. You should have 720 ways that we can select all 6 molecules. Is it okay? All 6 molecules. Có 720 cái cách sắp xếp khi mà ta chỉ có đúng 6 cái phân tử. Được không ạ? Có nghĩa là gì ạ? Một phân tử nó có thể ở đây này, nó có thể ở đây này, phân tử thứ hai nó có thể ở đây hoặc ở đây này, phân tử thứ ba có thể ở đây hoặc ở đây. Thế thì có tới 720 cái cách sắp xếp. Được chưa? This is only the first step. Có 2 bạn ngủ gần này, bàn đầu này, tươi hết nhỉ. So, but the calculation, the number 720 is when we consider that all the 6 are different. All the 6 molecules are different. Here we consider that all the 6 are similar. Yeah, similar. It means that, okay, I do not differentiate the molecule. So, maybe I overcount the number of microstates of my system. Maybe one configuration I count it twice or 3 times. So I have to reduce it. So to get the number of different arrangements, I have to use this formula, which is the multiplicity of configuration. This one is a very famous formula in probability. I don't know if you already learned about it. Các bạn tính ở cấp 3 học một chút về statistics chưa nhỉ? Rồi đúng không ạ? 2 công thức này ít nhất là ta phải biết đúng không ạ? Cái công thức này là ta tính cho cái này giai thừa của 6 đúng không? Nên tiếng Việt tôi vẫn nhớ giai thừa của 6 thì ta chỉ tính là tôi tính tất cả các trường hợp có thể xảy ra mà tôi chưa tính tới cái độ lặp lại đúng không ạ? Và cái công thức của nợ này thì nó tính là ok, bây giờ tôi muốn thực sự là tôi muốn xem là có bao nhiêu cái trạng thái hay bao nhiêu cái arrangement. We want to know how many different arrangements. Yeah. Then we should use the multiplicity of configuration. So this expression, we know it, right? Here, this is the number of molecule that we have in one half. This one we have in the other half, and this one is the total. So we should have this. Is it okay? If we use this formula, then we see a different thing. For this configuration, the first one, we see the number of microstate of this configuration is only 1. Okay? Remember once again what we call the microstate, which is the possible state that the system can take. So this one has only 1 number of microstate. Good. This one has 6 number of microstates. This one has 15. And this one, you see this one, the number of microstate for this to happen is 20. This one corresponds to what? This one corresponds to the case that my molecules are arranged equally in half. In the 2 halves. In the 2 halves. You see? In the 2 halves. So we know that, okay, this one is the most probable configuration that my system can take. So here I consider only 6. Only 6. Okay? But I already know that for the configuration 4, this is the most probable configuration that my system can take. For example, here, if I calculate 31% of the time my system can take this configuration. Okay? This configuration. 31.3% of the time. Here I consider only for my system of 6 molecules. If we consider our real life, for example, this auditorium is a box. How many molecules do we have? How many molecules? A lot, right? A lot of number of moles we have. Then this number wind comes very close to 100%. It means that in mostly 100%, we have our gas molecules that are distributed evenly in this room. Good? That are evenly distributed in this room. It will not, my gas molecule will not just lie in this corner, but it will go everywhere. Otherwise, only people in this corner will survive. Đúng không ạ? Ở đây chúng ta thấy này, chúng ta mới chỉ xem cái hệ của chúng ta có 6 cái phân tử, mà cái khả năng để cho cái khí này nó phân bổ đều ở trong cái hệ của chúng ta nó đã là cao nhất. Cái khả năng để cho cái khí phân bổ đều nó đã là cao nhất. Nếu như chúng ta xem trong thực tế ở một cái phòng này của chúng ta có bao nhiêu cái phân tử khí như vậy, đúng không ạ? Chúng ta có hàng triệu cái phân tử khí như vậy, thì cái con số này nó sẽ gần tiến tới 100%. Có nghĩa là gì? Nó tiến tới cái trạng thái là cái phân tử khí của chúng ta nó phân bổ đều ở trong hội trường của chúng ta. Nó không chỉ ở trong cái góc này. Đấy là cái tôi nói bằng tiếng Anh đấy. Nó không chỉ ở trong góc này, nếu không thì chỉ có người ở góc này sống thôi. Và chúng ta hiểu được vì sao lại như thế. So we can explain why in this room my gas molecules will not just stay in one corner. Why it is spread evenly. Okay? Does you understand here? You understand here? This one I already explained. Okay, now if we increase the number of n, we will see that the probability for this configuration and this configuration, okay, the two most configuration, the two extremes, are mostly zero. The bigger the number is, the bigger these values come close to zero. Is it interesting? So, of course, if you want to quantify Boltzmann-also derived a relationship between the entropy, here he called the entropy with the letter X. Yep. And the multiplicity of that configuration. So this one is the famous Boltzmann's entropy equation. The Boltzmann. But this is, remember, to calculate the number of possible microstates of the system, because he defines the entropy as the number of possible microstates of the system. So if we use this, we are able to calculate the entropy, the possible microstates of the system. Is it okay to hear? Now I invite you to do very quick this small exercise, very quick, because we have more things to discuss. So now you can explain why we have enough air distributed evenly in this room, right? Yeah. Because the probability for all of my molecules, all of my gas molecules, stay in only one corner. is zero. Yeah, is zero. It cannot happen. Cannot happen. Đúng không? Cái xác suất mà để cho tất cả cái phân tử khí của tôi nó dồn vào trong một góc kia là nó bằng không, có nghĩa là nó không thể xảy ra, không có cái khả năng ấy nó xảy ra được. Thế nhưng mà cái xác suất cho cái khí của tôi mà the probability for my gas molecules to distribute evenly is 100%. Cái xác suất mà cho cái khí của tôi mà phân bổ đồng đều là 100%. Thì khi xác suất mà nó là 100% thì chắc chắn nó sẽ xảy ra, đúng không ạ? Xác suất nó bằng không thì chắc chắn nó không xảy ra. Đó. So here I summarize it. We have only now, we consider a little bit bigger system. Now we have 100 molecules. Okay, 100 molecules. We want to know the configuration that I tell you, the evenly distribution of my gas molecule in both halves. Then I can see the configuration. Then I can calculate, right, by the multiplicity. Remember this one. It is close to 10 power 29. 10 power 29. Here when we consider only 100 molecules. 100 molecules. For the configuration of 100 in 1/2 and 0 in 1/2, this is only 1. You see? Here, once again, we consider only my system of 100 molecules. I already have this very big difference. It means that, okay, I have 10 billion times. Yeah? Then most of 100 million times, I will have this configuration. Only one time I will get this configuration, but in another universe already. Is it okay? So, you see, the case that the gas will be distributed evenly, yeah, compared to the case that my gas is only in one corner. It will have a very big factor. Very big factor. Good. Is it okay? Is it clear until here? So you understand the entropy as the number of possible microstates of the system, and you also understand why why one case should happen and not the other case. Right? If we base on the probability. Okay? So you can also understand why the egg, when it drops, it should go in that way, because the entropy increases. When you drop the egg, okay, you will increase the number of possible states of the egg. So the entropy will increase. The egg will be broken, and it cannot go to the initial state, because when it is broken, the system, your system, has more entropy, and it should go in that way. not the other way. Được chưa? Các bạn hiểu cái khái niệm này chưa? Now we go to the second way, and it has a direct application with our systems, our real life system, which is the engine and the refrigerator. Here we try to examine the second way to define the entropy using the macroscopic perspective. So in this, we define the entropy as the measure of a system's thermal energy per unit temperature that is unavailable for doing useful work. Okay? The measure of the system's thermal energy per unit temperature that is unable for doing useful work. Good. So you see, the bigger entropy is, the bigger the thermal energy is wasted. Okay? Because that energy is not used for doing useful work. So here, in this case, what we are interested in is to calculate the change in the entropy. The change in the entropy. Of course, the change in the entropy is the final entropy minus the initial entropy, and it is defined as the integral of the differential heat per the temperature. The thermal energy per unit temperature. You see? Thermal energy here per unit temperature. Is it okay? So, this is the change in entropy. This is the change in entropy. If you look at here, we can count that the entropy this time has a unit, right? Has a unit, which is joule, right? Because the heat is measured in joule per kelvins, because the temperature is measured in kelvins. Am I right? Yep. So when we look at here, we see that an entropy change depends not only on the energy transferred as heat to the system, this one, but also on the temperature at which the transfer takes place. You see? So it depends on two things. The heat supplied to the system and the temperature at which the transfer takes place. Good? Of course, when we have a very small change in temperature, then we should be able to have this approximation. The change in entropy can become the heat per the temperature in average. Yeah, the average change in temperature. Okay, when we consider that the temperature change is small, it's very small, then we can simply calculate the change in entropy in this one. Good? Okay, and there's another remark. The entropy is a state function. Okay, we call someone a state function. It means that it depends only on the states, on the initial and final states of the system. It does not depend on the path. Very nice. It depends only on the state, the initial state. It's just like the change in entropy of the first law. It depends only on the state. That's why we say that the state property or state function. The properties that depends only on the state, we call it the state property. So we have, for example, the change in internal energy, right? The heat is not a state function, right? The world is not a state function, but the change in entropy, the change in internal energy is the state function. Good? Here we have a problem. If we just look at here, okay? If we just look at here, there are maybe cases that we cannot apply this integral. We know that to be able to apply this integral, we should have a path. Okay? We should have a continuation path from the initial state to the final state. But if, for example, we consider the case of the free expansion, there's no path. It changes immediately from the initial state to the final state. So there's no path for us to integrate, to calculate the integral. But if we consider that the entropy is the state, we do not care about the path. And of course, we will prove that the entropy is the state property to be able to use that. So we do not care about the path anymore. Okay? Do not care about the path anymore. Chúng ta sẽ thấy cái vấn đề này khi chúng ta định nghĩa như thế này, mà nếu chúng ta muốn sử dụng cái integral này thì trong một số trường hợp chúng ta không làm được, bởi vì cái integral này nó yêu cầu là chúng ta phải có một cái đường đi, đúng không ạ? Từ điểm Y đến điểm F thì chúng ta mới lấy tích phân của nó được, đúng không? Với cái trường hợp ví dụ như là free expansion, nó làm gì có đường, nó chuyển trạng thái một phát từ trạng thái ban đầu sang trạng thái cuối. Đó, free expansion nó không sinh công, nó không lấy gì cả, nên nó chuyển trạng thái một cái thì nó sẽ không lấy được. Thế tuy nhiên nếu như mà chúng ta chứng minh được thằng entropy này nó là state property thì chúng ta không quan tâm tới cái quãng đường, tới cái path của nó nữa, đúng không ạ? Chúng ta chỉ cần biết là ok, trạng thái cuối là như thế nào, trạng thái đầu là như thế nào là chúng ta tính được. Okay, this is also the case for to find the entropy change of an irreversible process. Then we will replace the process with any reversible process that have the same initial and final state, right? So, if we have entropy as a state property, then any process having the same initial and final states will have the same change in entropy. Do you agree with me? Đúng không ạ? Nếu như chúng ta đã chúng ta chứng minh được là entropy này nó là một cái state function, thì tất cả những cái chu trình nào mà nó có chung trạng thái đầu và chung trạng thái cuối thì nó sẽ có chung entropy, đúng không ạ? Đúng chưa? Thì ta sẽ không quan tâm nữa là, thì lúc đó thì ta sẽ tìm cái cách nào dễ nhất để ta làm. And the easiest way to find the entropy change for an irreversible process is to replace that process with any reversible process. Okay, any reversible process. Okay, so you see the importance of proving entropy as a state function. We are going to do it together. Now I consider a reversible process. Okay, and in that process I have my ideal gas in equilibrium states. In equilibrium states. Good. Okay. Now we try to prove it. We prove that the entropy is a state function. If I consider the first law, okay, once again I will use the first law. This time I use it in the differential form. Do you agree with me that we can write in this way? Good. Then because the gas is an ideal gas, so now I start to rewrite it. This one, okay, equal this one plus this one. Okay, I start to continue. Here, what I want to find is to have the expression of the differential heat, because I want to replace this one. I want to prove that this one depends only on the initial and final state. So I have to eliminate this one, this integral. Here I have this. You agree with me? This is the differential work. This is the differential internal energy. Okay? Good? Now if I apply the ideal gas, law, what do I have? Good? So this, you see already the expression of the change in the change in entropy, right? If I divide this one by temperature, I replace because PV equal nRT, right? Then P equal this one, and R T over V. But because I divide with T, it becomes nR over V dV. Good? And here we have nCV dt over T. Do you follow me until here? Good? Then if this time I take the integral, what do I have? This time I take the integral for both sides. This is what I have. This is what I have. Do you agree with me? So you see here, This is the definition of the change in entropy. This is the definition of the change in entropy. This is the expression that we developed if you saw the two expressions, this one and this one. What do you have? This one, okay, I have a mathematical solution, and this one I have this mathematical solution. We can see here that this one depends only on what? Depends only on the initial and final volume. Right? This one also depends only on the initial and final temperature. So the change in entropy here depends only on the initial state, am I right? And the final state. So once I already established this formula, I can be sure that my change in entropy is really a state function. Good? It's really a state function. Is it okay? Is it okay?
Yes.
Good. I summarize a little bit. Here, this is the way we define the change in entropy. Okay? Using this integral. Đây là cái cách mà chúng ta định nghĩa entropy và cho nó có cái integral này. But for irreversible processes, sometimes we cannot use this integral. So the most special case I take for you to understand is the free expansion. Right? The free expansion. Because in free expansion everything equals zero, we cannot use this integral. Một trong những cái ví dụ điển hình của cái irreversible process ấy, của cái quá trình không thuận nghịch ấy, chu trình không thuận nghịch ấy, là cái giãn nở tự do, đúng không ạ? Khi nó giãn nở ra rồi nó có quay lại được đâu. Thế thì các bạn có thể thấy là ở giãn nở tự do, so you can see that in a free expansion, because everything equals zero, no change. Ở giãn nở tự do thì các bạn có nhớ là tất cả nó bằng không mà, thì cái này nó đâu có tính được đâu, đúng không ạ? Thay đổi của so the change in temperature is also zero, the heat also zero, everything is zero. Thì ta không thể dùng trực tiếp cái thằng này được, đúng không ạ? Với rất nhiều các cái chu trình thuận nghịch, chu trình không thuận nghịch khác, ta cũng không dùng được cái biểu thức này. Thế tuy nhiên, however, if we can prove that my entropy is a state function, tuy nhiên nếu chúng ta có thể chứng minh được là cái entropy của chúng ta nó chỉ phụ thuộc vào trạng thái, then we can easily replace any irreversible process with another one. The process, any process that we well know, that we can establish, that shares the same initial and final state, then we can solve the problem. Tuy nhiên với cái vấn đề ví dụ như vậy thì chúng ta có thể thay các cái chu trình không thuận nghịch bằng các cái chu trình thuận nghịch mà chúng ta biết, các cái chu trình mà nó có cùng điểm đầu và điểm cuối, thì chúng ta có thể tìm được cái entropy của cái chu trình không thuận nghịch đó, được không ạ? So it depends only on the initial and final states. For that reason, that's why it is important for you to remember the way to establish this formula. Good. Now I invite you to solve this question, this exercise in 5 minutes, and then after that I think we can take a break. Okay, and then we go to the second law. Chúng ta học tới 10 tới tầm 10 rưỡi.
So, I propose that we take a break then. Yes.
Yes. Take a break.
Otherwise, it will not be enough.
Okay, 5-minute breaks. 5-minute breaks. After this, after this exercise, please, we take a small break and only small break.
Bạn nào lạnh và tắt của tôi điều hòa.
Lạnh quá.
Mà thế thì được.
Và chế độ ấm.
Chắc là hình như bên
Và điều hòa ấm em.
Okay, please.
Và điều hòa ấm.
Here.
Và lo đi fan.
We have an irreversible process. Tập trung ạ, nhanh ạ. Ta chưa nghỉ đâu ạ. Irreversible process here. In this half, okay, in this half, I have this block with higher temperature. In this half, I have another block. This one is a lower temperature. And if I remove this shutter, then what will happen? I will have the thermal equilibrium that will happen, right? And this one is an irreversible process. So you know that this is an irreversible process because it cannot go to the initial state anymore. Because we have an increase in entropy. Because we have an increase in entropy. So, how do we calculate the entropy change? How do we calculate the entropy change in this case? Here, this is what we have. The initial temperature of both objects, and here this is the final temperature when it comes to the thermal equilibrium. And we know this also. We know this. Ổn quá. We start from the definition. Very easy, okay? So what we have, we know that the heat actually is mc delta T. The differential heat is this one, mc differential temperature, right? Good. We divide it by T and then we solve this formula. Is it okay? Then we will have this one. This is the expression to calculate the change in entropy. of each object. Then we calculate the change in entropy of the object on the left. We calculate the change in entropy of the object on the right. Then we see that the net change in entropy of my system consists of both objects. We will see that there's an increase in the entropy, and this one, if we quantify it, it is 2.4 joule per Kelvin. Later on, you will see that the entropy of a closed system, okay, will always increase. It never decreases. It always increases. So this kind of questions is a very good warm-up for you, for this chapter. This is the easiest exercise that we can think of in this chapter. Now we take a very small break, otherwise we do not have much time, 5 minutes. Okay? And please, only 5 minutes, otherwise we cannot finish it in only 20 minutes. Okay, we continue. Otherwise, we do not have time. Please, we continue directly. So, we examine another problem that in this case, you cannot use the integral. Okay? This is also an irreversible process, but you cannot use this case the integral because this is a free expansion. This one, once again. Now I have 1 mole of nitrogen gas, okay, which is contained here. When I open this here, we know that the entropy will be changed, but we cannot calculate directly. You cannot, of course, calculate this one. Okay? When everything equals 0, the change in temperature equals 0, the heat equals 0. Am I right? Okay, you cannot calculate this. So, we should find another way. We should find another way. Yeah, so we should replace by irreversible process, which is my free expansion, with a reversible process that provides the same change in the volume. Here we have the initial volume. Okay, it's half of the final volume because here equal this one. So here, then the first step, because we cannot apply directly the formula, we have to replace that process. We have to replace that process with the ones that having the same conditions, the same change in volume. Okay. Then the temperature of the gas does not change in our case. Good. Okay. Then we should be able to replace it with an isothermal expansion. This is a smartest choice. We replace an irreversible process, which is the free expansion having no change in the temperature, by a reversible process. Okay, and my reversible process should have the same parameters than the irreversible process. So it should have no change in temperature, and it should have this change of volume. So this is the smartest choice, because we know that in this case we can use the formula of a thermal expansion, isothermal expansion, which is this one. In this one, we are able to calculate the heat done by an isothermal expansion. The choice is yours, okay? But we should choose what we are able to calculate. Good? Then, if we do like this, we are able to calculate, because we know that, okay, I can replace the heat like this one. Okay? And if I calculate the change in entropy, then my expression becomes only this. And for this, I know how to calculate. You see? This is why I say that we should prove that the change in entropy is a state function for that reason. Is it clear? So we replace my irreversible process, the one that we cannot calculate directly using the integral, by something that we know that we are able to calculate it. And for a free expansion here, we know that for a free expansion, there's no change in the temperature. The easiest way for us is to choose the isothermal expansion. Yeah? Because this is also an irreversible process with no change in temperature and so. Good. Is that okay? I think you need a little bit more time when we do tutorial classes, for example. For some of you already understand, some of you not yet. Anyway, we will go to the second law of thermodynamics. The second law of thermodynamics is very easy. It says that if a process occurs firstly in a closed system, the entropy of the system increases for irreversible processes and remains constant for reversible processes. It never decreases. Okay? It never decreases. This is the second law. If a process occurs in a closed system, not open, okay? In an open system, of course, the entropy might decrease. But if we consider a closed system, for example here, if I consider this one, okay? If I consider a closed system of only my object on the left, of course, the entropy will decrease. Okay? The one on the right might increase. But if I consider a closed system of both two objects, then you will see that the net entropy change will always become positive. Good? Will always become positive for that reason. So, we try to prove it. Now we consider a closed system. This one we know, right? I do not explain my system again because I use always the same thing. Now, the entropy change for the gas which loses heat will be this one. Okay? This one for the gas which loses heat, and the change for the reservoir which gains heat. Reservoir. Yeah. Reservoir. You should learn it because this is originated from French. My reservoir, I'm sorry. Reservoir. Nghe see? Có 3 chữ R trong từ này. Tiếng Pháp nó phát âm rất khó. Reservoir. Yeah, reservoir. So, the reservoir. This one, of course, we should have this, right? Because we consider a closed system. Then the net entropy should be 0 for sure if we consider no loss. Because here we consider no loss between my system and the environment. So the heat can only be transferred from the gas to the reservoir and so on, and vice versa. Good. Now, this is the entropy postulate, we know it, and the expression of the second law is simply like that, right? It's simply like that. Change in entropy equal or bigger than zero for a closed system. Chú ý nha, nó phải là closed system nha, chứ không là nhiều bạn vẫn hỏi thế nó vẫn increase đây, bởi vì nó không phải là closed system. Now we consider the engine. Here we come to very interesting part. We examine two applications, two famous applications. The entropy in real world, we consider the engines and the refrigerator. Here we consider the heat engine. Normally an engine is a heat engine, but we call it in short the engine, right? Every engine is a heat engine. The heart of every engine is a working substance. For example, in your motorcycle, we use the diesel, gasoline, okay? And the engine should operate in a cycle. So we change the temperature, the pressure, the volume of the gas, and then it goes inside a fixed volume, and then it comes back to the initial state. We call it a cycle. You can see, okay, there are 4 strokes and something. Okay, this is a cycle containing 4 steps, different steps. 2 strokes, so a cycle containing 2 steps for it to go to the initial state. Động cơ 4 thì, động cơ 3, 2 thì đấy. Okay, here. The strokes, which is the process, okay? Good. Of course, the engine, what we have before we started with the steam engine, you know already, the revolution of the industry comes with the steam engine. Now we have a lot of other engines. Now we have the gasoline air mixture, and this is still the dominant engines that we have until today. Maybe we wait for Tesla to replace our engines, but we have to wait maybe several decades more. Okay, now I consider the Carnot engine, which is an ideal engine. All processes are reversible. No wasteful energy. Okay? Carnot engine, an ideal engine. All processes are reversible. No friction. Good. We study the Carnot engine because this is the best at using energy as heat to do its full work. We will see that no real engine will go beyond the Carnot engine when we talk about the efficiency. So this is the diagram of a Carnot engine. Here we have once again what we call the hot reservoir, and here what we call the cold reservoir. Good. So the purpose is to transfer the heat from the hot reservoir to the low reservoir, to the cold reservoir, and here the work will be done by the engine. Okay, here we can see the 2 black arrowheads here on the loop. It suggests that the working substance operating in a cycle. Okay, So here we can have the heat transferred from the high temperature reservoir or the hot reservoir, okay, at temperature TH to the working substance, and QL, okay, is the heat transferred to the cold reservoir. Good. And here, this is the work done by the engine, of course, on the environment or something, to run the wheel. Now, we can establish the diagram for the Carnot cycle. For the Carnot cycle. Here the Carnot cycle, okay, will be considered of two isothermal processes. This one, and two adiabatic processes, this one and this one. So this is the diagram, the PV diagram of a Carnot cycle. Two isothermal processes and two adiabatic processes. Good. Then, if okay, here I just explain this, but you know that. Okay, now we go to the work done. The work done by a Carnot. So you agree with me that the work done is actually the heat, the difference in the heat, right? Because here we use the heat extracted from the hot reservoir, okay? And that heat when we go to the cold reservoir, and one part is to perform the work. So the work is actually the heat here. Good. Then the entropy change. If we write the entropy change, it should be this one, right? The entropy change is actually the entropy change of the hot reservoir plus the entropy change of the low reservoir, and we replace by this one. You agree with me? When we continue, when we say that this is a state function, then the change in entropy for a complete cycle should be 0. Am I right? Because, okay, for a cycle, complete cycle, the initial and the final state is similar. So we should have this. It means that we have this one relationship, we have this one. So we see that more energy we see that because the temperature of the hot reservoir is higher than the temperature of the cold reservoir, then this one should be bigger than this one. This one should be bigger than this one. We see that more energy is extracted as heat from the high temperature reservoir than it is delivered to the low temperature reservoir. And if we consider the efficiency of the Carnot cycle, we say the Carnot cycle, okay? Then it should be this one. Remember that the efficiency is always the energy we get. Per the energy we pay for. I told you one time during my tutorial class, what we get is the work, right? And what we have to pay for is really the heat extracted from the hot reservoir. So this is this one. And this one, you replace the work by this expression. You should be able to have the expression to calculate the Carnot efficiency. Maybe this one or this one. Is it okay? Until here. So this is the efficiency of a Carnot cycle. And no real engine can go beyond this efficiency. Here we can examine, for example, the Stirling engine, another process. In the Stirling engine, we have two isothermal. Okay, Stirling engine, two isothermal. Here and two isochoric processes. And if we establish it, we can see that this one, yeah, will have an efficiency that is smaller than the Carnot cycle. The Carnot cycle is the best in using heat to perform work. Here, this is the Stirling. The Stirling. Having this one, if you establish it, you will see. You will have a final formula. And when you compare with the efficiency of Carnot cycle, you will see that, yeah, it cannot reach the efficiency of the Carnot cycle. I skip this one. We do not have time. I invite you to do it at home. Now we go to the refrigerator. Bạn nào đóng hộ tôi nốt cửa đi, không thì các thầy xông vào, các thầy đuổi tôi ra chết giờ. 2 phút nữa thôi ạ. For the refrigerators, we can consider it as a reversed Carnot engine. So in a Carnot engine, we use heat to produce work, right? This time is different. We use work to transfer the heat from a cold reservoir to a hot reservoir. So here, this is what we have inside of my refrigerator. Here, this is what we have behind my refrigerator, which is hotter because we already use work to transfer some amount of heat here. That's why it is becoming colder and colder. If we consider this, I once again consider the efficiency of the refrigerator. But for the refrigerator, we use the word coefficient of performance. Okay? So this is the efficiency. But for the refrigerator, you use this word. So this is what we want, is the heat to be extracted from this cold reservoir. And what we have to pay for is the work. Now this time, okay, this time, the work is still this. Then we should be able to have the coefficient of performance for the Carnot refrigerator, which is this one. You agree? Good? Here I do a small comparison to prove that the efficiency of the real engine cannot go beyond the Carnot engine. Now I assume that I have an engine. Giống như toán vậy. Tôi giả sử là có cái thằng lớn hơn đúng không ạ? I suppose that I have an engine with a bigger efficiency. I try to prove that my assumption is wrong, right? Here I also assume that I have an engine that is having an efficiency that is bigger than the Carnot engine. I try to prove. So I try to connect this engine with my Carnot engine. I try to connect it. I try to connect my engine with the Carnot refrigerator. Then the work done by my engine is used to run my Carnot refrigerator. Okay, so I should have this one. Then what I see is that there will be no external work performed by my system, because this one, is already done to move this heat from here to here. Good. Now, if this this one is true, I should be able to write this, right? W over QH, which is this one here, should be bigger than W here over QH here. This one is the Carnot cycle, and this one is my real engine. Then we should know that this one should be bigger than this one. The heat of my Carnot engine should be bigger than the heat of my real engine. Good. So, because the work here is used to run the refrigerator, Carnot refrigerator. So, from the first law, I should have this. Or, if I move on QH to one side, I move on QL to one side, I should have this one. I call it Q. This one should be bigger than 0. So what we see here, there's a problem. What we see here, we see that the energy transfer as heat from a low reservoir to a low temperature reservoir to a high temperature reservoir will require no work. Will require no work at all. So we have a perfect refrigerator. It means that we do not need work. We do not need work. If we say that this one exists, okay? If we say that this one exists, we should accept that we have a perfect refrigerator that works, that can remove the heat from a cold reservoir to the hot reservoir without any work. And this is not good. This is not good. If we continue, we can calculate, we can see that the change in entropy of our system becomes negative, and it is against the second law. If we continue to prove, we establish the change in entropy, we calculate the net change in entropy, we see that the change in entropy of our system, of the perfect refrigerator is negative, so it's not good. Then we can conclude that a perfect refrigerator does not exist. It also means that my assumption is not true. Okay? So here we already proved that any real engine cannot have an efficiency that is bigger than the engine. I think we have some small exercise here, but I will continue with you. All the lecturers will also continue with you in the tutorial class. I'm sorry that we do not have much time to finish it in a very good way, in very we have no much time to discuss, but we will have more time to discuss it during the tutorial classes. So thank you so much. I think this is the end of the lecture, not the end of the tutorial class. Okay? I'm still available for everyone in my office at 202 or via my emails. So please, you can send me the email. If there are something related to the thermodynamics, I will try to arrange my time to answer. So thank you so much for today. Thank you again. Cái đoạn cuối này thì hơi thiếu thời gian một chút, nhưng mà các bạn chịu khó nhé. Ta về đọc lại slide, cũng không có gì khó khăn lắm đâu. Cảm ơn các bạn. tôi vẫn đinh ninh là 10 rưỡi, không hiểu sao.
10 giờ 25 là vào K2 rồi, 10 giờ 15 đến ra là nghỉ ngơi cô đẹp. K2 là thầy nào nhỉ? Thầy Nguyễn Việt Dũng rồi, thầy Linia. Vâng. Bây giờ thầy vào.
Cao